Okay, so we have used the formulas to find the mixed strategy that should give us the highest expected utility for both row and column, and then we've calculated just straight out the expected utility for row and found that with this mixed strategy, row's expected utility is plus 4 1/3. And so since it's a strictly competitive game, columns will be minus 4 1/3. But we can, as you remember, there's some shortcuts. Because remember, on a mixed strategy that's truly in Nash equilibrium, neither player will have any reason unilaterally to change his or her choice of probabilities for the strategies. So all of the columns have to have the same expected utility, and all of the rows have to have the same expected utility under this particular mixed strategy. And in fact, they all have to have the same expected utility of plus 4 1/3 for row. So we could reach this value by just simply, for example, calculating the expected utility on R1. That would be the probability of column playing C1, 11/12 times 4, plus the probability of column playing C2, 1/12 times 8. And when we do this, we get 44/12 plus 8/12. And that equals 52/12. That is times 4, 4 with 4/12 left, 4 1/3. Exactly correct. Or we could calculate the value of R2. That is the probability of column playing C1, 11/12, times the value for row, 5, plus the probability of column playing C2 times the value for row, minus 3. That is 55/12 minus 3/12, 52/12, and so 4 1/3. Or we can calculate the value of the columns. Okay, that would be the probability of row playing R1, 2/3, times the value for row of that 4, plus the probability of row playing R2, 1/3, times the value for row, 5, and that's going to equal 8/3 plus 5/3, which equals 13/3, which of course equals 4 1/3. Or we can calculate the value of in this case, of column 2. That's the probability of row playing R1, 2/3, times the value, plus the probability of row playing R2 times the value, minus 3. And that's going to equal 16/3 minus 3/3 equals 13/3 equals 4 1/3. So you could have calculated this value any one of these ways, but here's a check to make sure that this is the correct expected value. It's the same expected value for every column and every row. So if they hit upon this mixed strategy, neither will have a reason unilaterally to change his or her choice of mixed strategies, because if he or she did, the other could exploit that mistake. Let me give you one example to show you this. Look at column playing 11/12 C1, 1/12 C2. What if column were just to look at and say, oh, why bother creating a device that's going to give me this probability versus this probability? Let me just decide to play C1 with a probability of 1. Notice then that if column made that decision, row could exploit that decision and always choose R2 and get an expected utility of 5 instead of 4 1/3. So column actually does better playing this weird mixed strategy, because if column were to just simply play C1 with a probability of 1, the value of the game for column would not be minus 4 1/3, it would be minus 5. And column would do worse, strictly, than by employing this chance device and playing this mixed strategy. Similarly for any other chain. This is the strategy, this mixed strategy that is in Nash equilibrium. If they hit upon this mixed strategy and continually play it, both players can do as well as they possibly can do in this game, given the payoff structure.